So in the last few lessons, we've discussed how we can take data set from one participant, for example, in this case, one structural image and a number of functional runs, and how we apply a number of pre-processing steps to the data. And then for every voxel of every run, we perform a single subject GLM. And then what I want to discuss today is once you do that, and perhaps you find out how to transform the functional data into a standard template so that you can compare across individuals. What I want to touch on today and discuss is really how do we then do a group analysis. So once we've done a first level analysis on everybody, how do we aggregate those data into one group analysis? And then what I'm showing here is the typical way in which an fMRI result would be pictured, which is a standard brain under and then sort of some pattern of activation from the group of participants. So when we're talking about aggregating multiple subjects, see what we're trying to understand, obviously, as you know well, is whether some kind of effect holds across our whole group of people. And see, the issue then is how do you tell whether something is significant or not? And as you certainly remember, the whole point of the classical way in which we address this question is to compare some effect to variability. And this leads me to what I think is sort of the most important aspect of this particular lesson, or sort of the most important insight underlying this lesson, which is the fact, in the words of Holmes and Friston, that classical statistical hypothesis testing proceeds by comparing the difference between the expected and the hypothesized effect, so whatever is our effect of interest, against the yardstick of variance. And see, crucially, what really matters the most, which is what we're going to spend quite some time discussing today, is what is the yardstick? Which yardstick of variance should you use when you're doing a group analysis? Because see, according to what yardstick you pick to compare your effect against, that will affect what you can and cannot infer from your data. So that affects the conclusions that you can draw from your data. Let me explain. So when we're looking at variance at the group level, there are different models that we can adopt. And as I said earlier, each one comes with a different inferential scope. Now, you could use what is known as a fixed effects analysis. And this is all about intra-subject variability. The idea is that here you're comparing an effect against the yardstick of how precisely you can measure that effect. Here, and I'll show this in a number of ways, but the idea is that subjects are fixed. The only variance that exists in this point of view is the precision, is measurement error. So your variance here really is the average measurement error across all of your participants. And importantly, each participant here is considered as fixed. Now, a different model is typically referred to as a random effects model. Now, this is all about inter-subject variability. And the idea is that the yardstick here is how much variability there is across different subjects. So you might look into subject A and look at their effect, and then subject B and look at what effect you get in them, subject C, et cetera, et cetera. And then you take the variance across the effects across all subjects. And see, the crucial insight here is that subjects are considered to be a random variable. In other words, there's a whole population of potential participants to your experiment. You just happen to have sampled randomly, I don't know, 20 of them. And so a random effects analysis takes into consideration the fact that you have, out of all the possible participants, all the population, you picked a certain 20 participants. So that's what I mean when I say that participants are considered to be a random effect. And so here the yardstick is the variance across the participants. And finally, if you put together fixed effects and random effects, you can do what is known as a mixed effects analysis. So this is an analysis where the yardstick is made of both the intra-subject and the inter-subject variabilities. In other words, the yardstick here is the sum of the fixed effects, so the intra-subject variability, the measurement error, and random effects, which is the variance across of the effect across different subjects. Now, let me show, what I'm going to do next is I'm going to show the exact same idea, but in two additional ways. Okay, so this was sort of the descriptive verbal way. Let me show it in a visual way. So if the black line is the real mean of an effect, the red line is your measurement. And as you can see, the only variance in here is measurement error. How well you're approximating the black line at each measurement. Right? That's the only source of variance in this picture. So this represents a fixed effects analysis. Right? The variation, the only variation is really measurement error. How well can you approximate, how well can you sample and capture the black line? Importantly, the response in of itself, the black line, is considered to be fixed. That's why we call it a fixed effect. And I'll give another example of this a few slides down. In other words, here really what you're saying is you're inferring that a subject's response is significant with respect to how precisely you can measure it, a fixed effects analysis. Now compare that to a random effects analysis. And again, as I said earlier, the key insight here is that although there's a population mean, which is the black line that you're seeing, the mean of each participant varies randomly around the population mean, around the gray, the black line. So the source of variation here is how much does each subject respond to this particular task. And this particular how much is considered to be a random variable. Again, you could have picked anybody from the whole population. You just happen to have picked these 20. So you consider the 20 means that you actually measure, you just consider them to be a random variable. So this is a random effect. Of course, what is fixed in this case is the population mean. And that's just whatever is the true mean. Okay? So in a random effect, the variance comes from the fact that different participants just have a different mean on, for example, bold activation in response to some task. And that mean for each participant just distributes randomly around the true mean of the population. So there's the mean of the population in black. You sample 20 people. The effect in each of these 20 people varies randomly around the population mean. And finally, if you put the two together, you're getting a mixed effects analysis. There's a true mean in black, then there's the participant mean in green, and measurement error in red. So now there are two sources of variation. The fact that the participants vary around the population mean, and there's measurement error for each participant. Right. So, and then here, again, much like in the previous, in the random effects, the response magnitude, so again, each subject's mean is a random variable. Now let me show this in a third way, which is sort of the algebraic mathsy way. Now, in a fixed effects model, what you're trying to do is you're trying to model every time point for subject I. So in other words, time point j for subject I, right? The value of a given voxel of a given subject at a given time point, is a function of whatever is the subject's mean plus some kind of measurement error. That's the fixed effects, right? And so in this case, the variance fixed effects would be over a group of individuals, sigma squared within measurement error over big N, which is the sample size, and little n, number of observations per participant. But of course, you realize that the DI is in of itself a random variable. It's not a fixed variable, right? Again, we pick 20 people to participate in our experiment out of a large population. Which 20 people we picked out of the population is a random variable. So really, your mean DI, the mean effect in you, participant I, is really a function of two things. It's a function of the population effect. After all, your mean has to depend on what is the population mean, plus or minus your, some variability. Right? So there's the population mean, and you, participant I, will vary somewhere around that mean. So in this case, the random effects variance would be the between subjects variance, sigma squared between, divided by sample size. And finally, mixed effects is exactly what you think. If you just see that the I, right, if you take it and you just replace it in the fixed effects model, so you take this and you put it and you plug it into the fixed effects model, you get exactly the mixed effects model, where the value of for participant I at time point j, the value for one voxel of participant I at time point j is really a function of three things. Whatever is the population effect, plus or minus your unique variance around the population, so whether you happen to be a little bit above or a little bit below the population mean, plus measurement error. Now this is the fixed effects model. I'm sorry, this is the mixed effects model. And often we just sort of abbreviate the sources of variance into eta, with eta being the sum of the between subjects variability and the within subjects variability. In other words, the mixed effects variance would be sigma squares within divided by sample size times number of observations plus sigma squared between over sample size. And of course, if you look at this, it should also be clear that if you want to maximize, if you want to minimize variance at the group level, would you rather give each subject more time points, so sample more each subject, or would you rather sample more subjects? Which would you pick?